without too much more ado, I think we'll get started for the day. So just like to bring up our first speaker, Dr. Nick Williams. Quick bio here. Nick is a principal geophysicist for HPX, where he develops and applies 3D geophysical strategies for exploration. He specialises in integrating geological and geophysical models and data in 3D. Prior to joining HPX, Nick was principal geophysicist for Ivanhoe Mines Group, where he worked on the geophysics of Oyu, Platreef, PGE-Ni-Cu-Au, and other major deposits held by the group. Before that, he spent 10 years working at Geoscience Australia, first analysing geochemical and structural controls and mineralisation, then developing regional scale 3D geophysical modelling methods, and finally managing their regional scale airborne EM acquisition program for energy exploration. He has a PhD in geophysics from UBC, a Bachelor of Science and Honours degree in Geology from Codes at the University of Tasmania. Welcome, Nick.
Thanks, Brendan. Thank you all for showing up on a classic Vancouver day at such an early hour. I'm glad the buses were working. What I'm going to show you today is a case study where we can use advanced gravity and magnetic modelling methods to add real value to an existing resource. In this case, it's the Platreef PGE-Ni-Cu-Au project in South Africa. First, I want to thank my co-authors, Barry Devl and the team from Ivanhoe Mines. In particular, I'd like to thank the Ivanhoe Mines geologists for having the confidence to take some of these geophysical concepts and drill some large step-out deep holes to test these ideas. And I think it paid off for them in a big way, but without their courage, none of this would have happened. I have to start with the usual disclaimer about forward-looking statements from Ivanhoe Mines. So, the outline of what I'm going to tell you about today is I'm going to introduce you to the Platreef PGE-Ni-Cu-Au project up in the Limpopo province of South Africa, about a 3-hour drive from Johannesburg. I'm going to talk about the geology and the physical properties, and then I'm going to show you how we use those in the magnetic and gravity inversions to get some real predictive value. And I'll finish with my conclusions. So the Platreef project is located on the northern limb of the Bushveld igneous complex. The Bushveld complex is the largest layered intrusion in the world. It covers some 60,000 square kilometers in area and produces 60% of the world's platinum every year. Mostly from the UG2 chromatite and the Moransky Reef, which are outlined in white on this map. The Bushveld igneous complex intrudes the Kapval craton and is emplaced on the Transvaal supergroup metasediments, shown in yellow. And the igneous complex includes a set of morphelsic units on top of a layered mafic intrusive. That we call the Rustenburg layered sweep. And that's where all of the geology that we're going to be seeing in Platreef is located. It's divided into a lower zone, the critical zone, which hosts most of the mineralization throughout the Bushveld complex, the main zone, and an upper zone. Zooming into the project area, Platreef is located about 12 kilometers northwest of the town of Mokopane. The Anglo-American Mogalakwena mine is another 10 kilometers to the north, and it's been operating since 1993. And the Platinum Group Metals Waterberg platinum deposit lies another 100 kilometers to the north at the far northern tip of the northern limb of the Bushveld complex. The stratigraphy here is really quite simple, with the Transvaal supergroup sediments on the east and a southwest dipping series of stepping up through that stratigraphic column, isolated occurrences of lower zone, then the critical zone with mineralization, the main zone and the upper zone. But really, we're looking at that main zone, critical zone part of the Rustenburg layered sweep. At Platreef, that critical zone is up to 200 meters thick. And as you can see, it's divided into a complex stratigraphy of cyclic units of norite and other pyroxenite phases with chromatite stringers and mineralization interspersed throughout that sequence. The ultramafic rocks in the lower zone typical Hartsbergites and Dunnites. We move up into the critical zone, and you can start to see this cyclic series of more leucocratic phases, norites, pegmatoids. If we zoom in, we can see some gradational, or some sharp transitions with some gradational cumulate changes. We get an orthosite, then a chromatite band, and then a coarse norite that becomes more leucocratic as we move upwards. And that's where the sulfides are hosted. Then the main zone is has even more plagioclase with gabbronorites and anorthosites. You can start to see there's a real visual change as we move up the sequence that may manifest as a physical property contrast. The overall architecture of the project looks something like this on a schematic southwest to northeast cross-section. We have a thick accumulation of main zone rocks, 1,000 meters or even more. Below that is this thin critical zone, 200 meters thick perhaps, where all the mineralization is hosted. Underneath that we have the lower zone emplaced unconformably on the transvulsive group. If we zoom right into that contact between the main zone and the critical zone, in this case showing a scale of about 50 meters through a drill hole. We have the main zone rocks, which are barren. We hit that contact with the critical zone, and instantly we've got mineralization in a peroxenite, and then we step down, we have some chromatite stringers, and we step into another peroxenite that has even more mineralization. So really, it's right at that contact that we're interested in looking. The resource at Platreef, there's an indicated resource of nearly 350 tons of a combined platinum, palladium, gold, and rhenium equivalent of around 3.7, 3.8 grams per ton. It's a huge deposit, it's laterally extensive. The indicated resource is outlined in green here, but there are lots of large extension areas outlined in blue, and two of those major extensions have been defined purely based on the geophysics and aggressive step-out drilling. To give you an overview of the data that's available to us on this project, the orange area here is that indicated resource. It covers about 4 square kilometers in area. We have an aeromagnetic survey, we have a Falcon gravity gradiometer survey, and extensive drilling. To give you an understanding of the timeline of exploration here, there was initially some mapping and shallow drilling that defined an initial resource before 2007. Step-out drilling from that program defined this Platreef underground resource, which is what is currently they're building the mine around. And it was at this point where the geophysicists got involved. And we did our first magnetic inversions and our magnetic modeling, which allowed us to predict a continuation of the reef and justified another major step-out program to the southwest. With that in hand, we flew a Falcon gravity gradiometer survey, modeled that, and came up with another extension zone which we were able to track with extensive drilling out to the south. Looking at the physical properties from all of those drill holes, here I'm showing the critical units within the main zone, the critical zone, and the lower zone. Most common units. The horizontal scale is the same. You can see that right away there's not much of a contrast in the magnetic properties between the 3 zones. If you look subtly at the statistics, there is a steady increase going down the stratigraphy, but it is subtle. It's probably too subtle to map consistently. However, what we do see is there is a major physical property contrast in those magnetic properties to small, more isolated units, the ultramafic rocks, the Hartsbergites, and the dolerites. Wherever we get those units, we're going to get a kick in the magnetic properties. Fortunately, we do get most of those units in the lower sequences. So there is a general trend from lower mag responses at shallower levels to stronger magnetic responses in the critical and lower zones. But there was an excellent paleomagnetic study done on the Bushveld complex just before we started doing this work. And reviewing that showed us that there is extremely strong remnant magnetization throughout the Bushveld complex. We're talking about the northern limb here, and there was less data available for the northern limb, but looking at the eastern limb or the western limb had the same story. What we see in the northern limb is that main zone has strong reverse polarity remnant magnetization with a Königsberger ratio of 60 or even as much as 100, which means remnant magnetization intensity is 60 to 100 times stronger than the induced susceptibility. In the critical zone, it's much more well behaved. The Königsberger ratio is around 1, around the crustal average, and it has a normal polarity. But modeling that main zone, which is up to 1 kilometer thick above our ore deposit, is going to be critical, and treating that remnant magnetization is essential to get a good result here. If we look at densities, the same plot with the same units for the same 3 zones. This time you can see there is a major density contrast between the main zone and the critical zone. Remember, the mineralization is sitting right at that critical zone contact. So that is extremely favorable for using gravity as an exploration tool here. When contrast is on the order of 0.3 grams per cc or 10%. I should point out that there's no clear association of density and grade. We're not pretending that we're mapping grade here, we're just mapping the contrast in the lithology densities across that contact, and that's good enough for us. We can look at a couple of Y-line logs down a couple of boreholes to see how that spatially, those properties spatially relate. We have magnetic susceptibility on the left and uncalibrated Y-line density on the right. You can see, and I've plotted various moving average windows over those to smooth them out. But you can see that the magnetic properties are extreme in that southern part of the lower part of the sequence, but they're for small isolated lithological packages, whereas the densities show a consistent increase in density contrast as we go through that contact zone. So we started with the magnetics, which had been flown in 2004. It was available, and we could just jump in and use it. This is a residual TMI magnetic grid, and many of you may recognize these zones of really extreme high TMI response next to extreme low TMI response. And those are diagnostic of having strong remnant magnetization, can be diagnostic. We see it in several areas in this grid. So we know that remnant magnetization is there from the paleomagnetics. We can infer it from this grid, but if you missed it, if you still didn't know, you'd run an inversion that assumed there was no remnant magnetization. In this case, I used the Geophysical susceptibility inversion, and you'd get a model. No problem getting a model. But that model doesn't bear much resemblance to the geology that we know. We see these stripes with these lobes of extreme magnetic susceptibility shooting down to either side, values of 3, 5, 10 SI units, just completely unrealistic, with a non-magnetic center. And that is another hallmark of remnant magnetization. So we need a different method. So we applied the Geophysical magnetic vector inversion to this same data set. What this does is it solves for a full 3D magnetic vector in every cell in the model. That allows it to include induced, remnant, and demagnetization effects. But it's much easier to represent that as a scalar magnetic amplitude. So that's what I'm showing here. It's just the magnetic intensity in every cell. You can see it's got a very different shape. Instead of a low surrounded by highs, we've got a confined magnetic high running along that trend. So looking at the same section slice that I'm going to show from southwest to northeast through the project, we can see on the left the susceptibility inversion, on the right the magnetic vector amplitude, and they're very different. You can see there are magnetic highs in about the same places, but they have very different geometry, very different character, very different values. But we have some drilling here already, and so we can see how the correlation between the drilling and the magnetic models works. We can make some interpretation about where that main zone, critical zone contact might be based on our existing drill holes. And doing this, we can see that the susceptibility model is just not right. We don't even need to look at it. We can use the magnetic vector amplitude with some confidence and start to make predictions about where that contact might go. And we made a prediction that the contact dives down to the southwest to much deeper levels. Instead of 1,000 meters, we're talking about 1,500 meters. And Ivanhoe Mines stepped out a kilometer from their nearest drill hole, drilled this new hole, UMT-081, based on this magnetic modeling result, and hit the mineralization exactly where we expected it to be, showing continuous mineralization over a much larger area. So that gave us the confidence to invest in the geophysics, and we flew a Falcon gravity gradiometer survey in 2012. Here I'm showing a residual vertical gravity grid of the survey. You can see there's a strong density band running through the middle, which looks like it might correlate with that density contrast that we're looking for. We can do a default density inversion, this time using the UBC GIF Grav 3D codes, and we can get a model, and we'll look at what that looks like in a minute. Looking on that same slice, we can see we get this large, dense body in the middle of the survey, in the middle of the project. And that makes a lot of sense. That's what we see. We know there's this large, dense body there. But we also have a lot more drilling now, and we know that we don't have all this dense material above that contact position. And that's main zone. We've got density measurements all along those holes. We've logged it. We know it's not there. So if this was your first inversion and you had no drilling, this model would be great, and you'd probably know where to drill the right hole, but we're not at that position. We want to know where are the extensions, what's the subtle inflections that we need to be targeting here. So let's put that geological information into this model. So we take our mapping and our drilling, we take the density measurements that we've acquired, and where we have them directly, we can paint them into the model to create a reference model of what we think the densities are. Where we don't directly have density measurements, we can use a proxy, we can use an estimate for each lithology based on those density measurements. We can paint those into the model where we've observed them, and then we can extrapolate them out using our information about the structural orientations and the strikes and dips in those drill holes. And we can assign some confidence to that extrapolation to say as we move further away from a drill hole, we're going to be less confident. And we can put that into the inversion. And what the inversion does is it modifies that input model in as little possible way to make it also satisfy the gravity data. So we get a result that satisfies the gravity data and matches our geological information. We can compare it to the default result, and these have the same color stretch, they show the same volume, the same area. You can see that where we've got mapping on the right, we're recovering those bands, as we should. We know they're there, why should they not be in the model? But you can also note that the density contrasts are much higher in the model on the right. We're emphasizing more subtle features, we're bringing out extra detail in the model. So this is what the inputs look like. On the left, we have the reference densities, our best estimate before doing the inversion, based on drilling. On the right, we have confidence. Where we move further away from a drill hole, we have less confidence. Where we have less sampling, where we don't have density measurements, we have less confidence. And where we don't have any drilling, we have no confidence. We can let the inversion do what it needs to do, guided by the gravity. And this is the result on that same section. And you can see that it's modified the model just enough to make it also fit the gravity data. I don't need to show you the predicted gravity response because it's the same. It's easy to generate a geophysical model that reproduces potential field data. That's trivial. But this also reproduces the geology. Comparing to the original default result, you can see that there's a vast difference here. But the model on the right matches what we know about the geology. We can make some inferences from that model. So just to give you a different representation of the same process, this is a 3D cutaway view looking to the east. The red squiggles are the schematic platinum grades down each of the drill holes that we had at the time. We have the drill holes, we have the geological information, we paint that into the model, we build up some constraints, we build up a model of what we think the density is, and we get a result. Now you can see on the right here, there's this big flat zone of density contrast being predicted in an area of no drilling. There's about 2 kilometre span there that hasn't been drilled, and it looks like it's relatively shallow depths, about 700 metres compared to the rest of the deposit at 1,000 metres. We can map that out and we can predict it as a surface across the whole project area. And this is what I've done. I've just gridded up the depth to that contact. You can see that we get a really complex topology to this main zone, critical zone contact. And there's a huge area down here, 6 square kilometres at depths of about 750 metres that had not been drilled. And so Ivanhoe Mines went in and drilled that, and drilled it with a series of holes, all of which were mineralised at the right depth. So here's a 3D model of what that surface looks like with the 4 different zones that I pointed out earlier. Pointing towards you now is the shallowest zone, defined by mapping and drilling originally. Then there's the step-out zone in here that was defined by the step-out drilling program. Then there was the zone that was defined by the mag inversions and the drilling that followed the mag inversions. And finally, there's this large plateau or shelf defined by the constrained gravity inversions that we went on to drill. But you can see there's more complexity, there are more inflections in there that we could be chasing. But this is an iterative process. We don't have to stop at doing this once. We can do it as many times as we like. The computer power is relatively cheap. And so we can take that model where we finished on the last slide, drill a bunch more holes, get density measurements on those holes, and plug them back into the model and get an updated prediction of where that contact surface is. And that's what we've done. We keep drilling, and it's looking very good. So coming back to the resource, what has geophysics added here? Well, those 2 lobes of inferred resource on this project, one defined by the magnetic inversion results, and the second defined by the gravity inversion results. Both of those were added by doing these advanced geophysical modeling methods. So in conclusion, I've shown you a case study from the Platreef PGE-Ni-Cu-Au project in South Africa, showing that geophysics can add real value to advanced projects. To do that, we've used all of the available information, the mapping, the drilling, the geology, but also the density and paleomagnetic studies are critical to make the right choices about what tools to be using. You need to understand if remnant magnetization is a problem and use an appropriate tool. But the physical properties also showed us that density was going to be the best at mapping that contact. And so we invested in a gravity survey to get that done. And we're constantly revising these results. This work is nearly 5 years of repeated visiting onto this property, this data set, and working it as they get new information and acquire new data about the property. Thank you very much.
Any questions for Nick? We've got a couple minutes.
Yeah, Sergey.
When you calculated the density from the density contrast, you said you used 2.91, but the main zone is 2.7 and the critical zone is 2.8. Why do you use 2.91?
The critical zone's more like, the main zone was more like 2.8 and critical zone was more like 3.1, and the lower zone is like 3.2 nearly. So basically that 2.9 came from a little bit of trial and error based around looking for what is the bulk density of all of the rocks in this project area. It's got nothing to do with the terrain correction density, because the terrain correction in this area is a tiny little thing at the top. We're talking a kilometre down. We're looking at the bulk density, and it's a good enough approximation to give us a model that makes sense geologically. Could certainly change it.
And how do you calculate the confidence for the constraint inversions?
Using confidence interval statistics, just calculating the confidence interval on a mean at 95 or 99%.
I've got a question, Nick. You showed one downhole wireline log, uncalibrated as you mentioned. How many holes did you have wireline density for? Was it a standard part of the logging process?
It was not standard, but we did have them in place before before the gravity inversions. But as I mentioned, it's uncalibrated densities, and so I don't know if you could see the scale, but those densities are more like the 2.8, 2.7 that Sergio was talking about, because they're not calibrated, they're not performing well in the ultramafic rocks. There's work that can be done to fix that, but then you also have to address the scale issue, because we're measuring at centimeter, decimeter intervals down that hole, but the model is looking at 50-meter cells. So how we use that effectively, we didn't use borehole logging. There are about 10 holes that had been logged at the time, and those 10 holes, we also had more standard density measurements, and we could just use those.
Fair enough.
Nick, was there any consideration of doing ground gravity instead of Falcon, or was there any kind of games played initially, cost-wise, time-wise?
There was some regional ground gravity on a fairly coarse spacing. The challenge here is that the area is heavily populated. So doing a detailed ground gravity survey through people's farms and houses was just a bridge too far, and it wasn't necessary given we were looking for a really big feature. We didn't need that kind of high resolution.
Were all the inversions based on the GZ?
Yes, I used the equivalent source conform GZ.
So any of the gravity gradient data, where did that come
No, at the time there were no gravity gradiometer codes that we felt that we could use to attack that problem. Looking at it now, I think it would be worth revisiting with gravity gradiometer codes.
You have a high gravity anomaly under the Platreef. Have you attempted to explain what causes that anomaly?
We're confident that most of it is just coming from these thick sequences of lower zone and mainly lower zone rocks. We have not found the bottom of the lower zone in this area. It's not mapped extensively. We have very little understanding on how thick the lower zone is, but we know it's dense and we know it's filled with ultramafic rocks. So I can easily envisage that a kilometer of those would explain that.
Thank you.
Well, if there's no more questions, I'd just like to give Nick another round of applause.
Thank you.